So as I said, I'm Anders Hildeman, and I will present some research work that I've done together with Phil Tier from the same department as I, which is data science and AI, and with Sylvia Makrovska, which is part of the I for AI trainee program that is sponsored by AI Sweden. We call this talk Unlocking Hearts by Locking Models, and you will understand that during the talk, I guess. So before going into any details, I will just tell you that what I'm actually trying to sell here is more the overarching approach that we used. So we will be talking about echocardiograms, which is a type of medical images. But we're in a setting that is quite common in other cases as well. And that's when we have a rather complex data modality. Labeling of data can be costly. Certain classes can be rare. In our case, it might be rare diseases. We have black box models with a lot of parameters, and we have like regulations on how to validate those, and those are quite strict. And our models should be easily communicated as well. So in some sense, this is true for all machine learning problems, I guess, but it's especially true when you're working with medical images for applications. So the type of data we're working with is echocardiogram. So that's ultrasounding of the heart. And that's really useful because ultrasounds are non-invasive, they're non-ionizing, and you have a nearly instant acquisition. So therefore, in clinical practice, it's really popular to use these to derive some medical metrics or medical parameters from those. So here you see one example. So you have a sequence. Sometimes we have stills, sometimes we have movie sequences of a heart beating. And you can take these acquisitions from different perspectives, and we call those views. So here you see 4 different views of the same heart. And the idea is that for some medical parameters, you need to look at from some special direction. Sometimes you need to look from several directions at the same time. So I'll be looking at 2 sub-problems with echocardiograms. Those are just examples here. There are a lot of other problems as well. So one is to automate or to detect views, because sometimes it's hard to acquire some views on some patients, and they get lost. Annotation might get lost. And we're working with trials with a lot of different patients. So this is actually a real problem. It's useful to be able to detect which view an echocardiogram belongs to. Another sub-problem is segmentation of an anatomical region. So this is typically necessary in order to acquire those later medical metrics. So here you see an example of a segmentation of the left ventricle that is done automatically or semi-automatically by professionals, where they basically outline the left ventricle in this case. And also this would be useful to do automatically of several reasons, especially when you're working with a large data set of echocardiograms from several patients at the same time. And then we have some general issues with, I guess, medical images in general. So first of all, it's a structured image. So a digital image is an array of values for each pixel. We're not particularly interested in a specific pixel's value. We're interested in some latent information, some structure in the image. And our eyes and brain is really good at finding these structures. If we look at this image, we will find edges. We will see the relationship between edges, and we will interpret that. We want the computer or the model to be able to do the same. And that's generally non-trivial, which means that we have to resort to black box modeling, typically neural networks. And such models have the problem of having a huge number of parameters, and we have no full understanding of how these parameters interact. And therefore, we can't regularize on them, so we can't really say what they kind of should have as values. And that means that we need even more data in order to acquire robust training and do a proper validation of that as well. Then we often have the problem of scarce labeling as well. So we need a medical professional to label these, as you saw before in this image, where we did the segmentation, and also for views. And of course, we need large data because we have a large number of parameters. But a lack of labeled datasets doesn't necessarily mean that we have a lack of unlabeled datasets. And this is where self-supervision is going to come into the play. And then finally, we're working with real people, and we want to approve their life. But there's also a risk that making the wrong decisions will have detrimental effects on their health. So therefore, we really have to have a good understanding of when our method works, if it doesn't work, why. So with this in mind, we looked at this and thought out this concept that we call ALAN. We're not certainly the first one to have thought up this concept, but I think we're the first one to have named it ALAN. And ALAN stands for Adaptive Locked Agnostic Network. So the basic idea is that we train some large black box model on unlabeled datasets using self-supervision. And then we lock those parameters to never touch those values again. And then we use simple intuitive methods on top of that. And these methods should have parameters that we can understand the meaning of, and they should be a small number of those as well, so we're able to train on scarce data. And we're also looking at different regulatory pathways to basically prove quality of the backbone model before choosing the application. So the idea is that we will use the same backbone model in the future for applications that we haven't even thought up yet. So what is self-supervision? So it's the idea of automatic feature engineering, basically. And before we had a talk about NLP, and that person said something about playing games with our sentences. And that's what I think he referred to was self-supervision. So we need to solve some puzzles. And the hope is that by teaching the model to solve these puzzles, it will find some inherent latent information in the data that we later can use for the actual problems we have at hand. And there's a plethora of different self-supervision algorithms, but we looked at this method called DINO, which stands for self-distillation with no labels. The idea is training without labels and distilling out the essence of the data, I guess. And the good part with this one, as well as some others as well, is that if your input is an image, your output will be an image as well. And the input pixel will be related to the output pixel while still using a transformer architecture to find dependencies between several pixels at the same time. So that's the good part about DINO. We wanted something intuitive, and the bad part with the output of DINO is that it's rather high dimensional. So if the input is an image that has a lot of pixels, and each pixel have 3 channels, typically like red, green, blue, the output will be that each pixel have a value in 384 dimensional space, which is not really intuitive to interpret, at least not for us humans. So therefore we used a method called Stego, built on top of DINO. And the idea here is to do self-segmentation, I think they call it. So do segmentation without telling our model what we're looking for. And they named it Stego. It's kind of shoehorned in there, but it stands for they had an acronym that was totally crazy, and I think they just wanted to get something that was dino related. So they got some kind of dinosaur, and that's why they have that name, and it's easy to remember. But the thing is, the output from the dino Stego pipeline is this self-segmentation of the input. So to the left here, you can see the input movie sequence, and then you see the output as a segmentation where we have all these small lumps of classes. And we refer to these as parcels instead of segments. And the reason for that is that typically these parcels don't exactly correspond to what a medical professional will be looking at in the image, but they kind of relate to it. And this is the main result of this proof of concept work, is basically that these parcels, like these parcels here, these colors, they stay robust between different patient acquisitions and between different acquisitions of the same patient and between different frames of the same sequence. So basically, we know that some region here, the brown part, will correspond to this part of the heart in more or less every patient we'll be looking at. And this is really strong results because it shows us that the result, or the model, is generalizing results between patients. And we can visualize it as well. And we can kind of understand what it's trying to do. And the domain experts can kind of understand what it's trying to do as well. And that leaves us with a lot of room to build up our own subsequent tasks to solve based on this. So you remember that we had this problem that we wanted to do segmentation of anatomical regions. So let's look at how we could do that. So basically, in the right image here, you can see my painting skills, and I've tried to highlight the left ventricle. And then you can just go to the left one and see, well, which parcels are within this outline. And you can get the list of, well, we have parcel, let's say, 3, 8, 4, 16. So those parcel classes would correspond to the left ventricle, and the others would not. And then we just join those and do some small post-processing steps. And we have an automatic segmentation of the left ventricle. So to look at results here, we have a dataset, a public dataset available that is called EchoNet-Dynamic. So it's around 10,000 sequences of echocardiograms from the A4C view. And it also has annotation of the left ventricle as well. So looking on the top here, we were able to, the only training we did here, the only time we had supervision was when we tried to acquire the list of which parcels correspond to the left ventricle. And then in the bottom, you can see 2 images of the segmentation compared to the true annotated segmentation. So blue corresponds to true segmentation, green to the predicted one, and turquoise is where they overlap. So they basically overlap quite well. And this is general among the whole population of this dataset. And to quantify this, we used the DICE metric, where 100% means perfect overlap and 0% means no overlap at all. And the mean DICE score of around 80% was what we acquired with this, just like this first idea of how we can do this segmentation. And that's a pretty good score. Then we were also a bit interested in, do we really need to train our backbone model in this self-supervised fashion on echocardiograms themselves? So we tried Dyno trained on ImageNet, which is not echocardiograms per se, but more general structured images. And as long as Stego was self-supervised, in a self-supervised fashion trained on echocardiograms, we could work and get pretty good results with the Dyno backbone trained on ImageNet. So we can do some form of transfer learning here as well. And that also suggests that we could use the same kind of backbone model to some extent, at least, for several different modalities of medical images. But then I also looked, so we actually don't have this result. This is the old presentation. Well, we also looked at training both Stego and Dyno on ImageNet, and that didn't perform that well. So the conclusion is that Stego should be trained on the modality we're interested in, and Dyno might not actually need to be, that might not actually be needed. And that's a good thing, because Dyno is the one that takes a lot of time to train and the one that needs a lot of a huge data set to train, while Stego is much more lightweight. But it's still a black box model, so we should train it in a self-supervised fashion on a rather huge data set also in that case. And then we had this other problem as well. We had the problem of echocardiogram view detection. And here we had to use another data set that had several views. So this one is called Tufts Medical Echocardiogram dataset number 2. So we had around 10,000 images from 4 different views. And then we classified using the Dyno output and 10 nearest neighbors. So from the training set, we took the 10 closest neighbors in Euclidean space to the echocardiogram with a known view. And we just chose the majority decision among those 10. And we got really good results. So on top here, we see that for each of the 4 classes of views, we got an accuracy in between 80 and 90%. And in total, we got around 90% of accuracy. And also here, transfer learning works pretty well. So Dyno trained on ImageNet gives us a similar result as Dyno trained on echocardiograms. I should say, after producing this presentation, we have some preliminary results where we also use these parcels for classification. And the idea is that to what extent different parcels are present in the image should tell us something about which view it is. And the preliminary results are really promising. And the good part with parcels are that, once again, they're easily communicated, easily understood by us, but also they have a much lower dimensionality, so they work better with classifiers of that reason as well. So in conclusion, clinical applications of machine learning with medical imaging have some challenges. We propose using the Allen approach, which ameliorates some of these, especially it makes it possible to work with scarcer data. And one of the bigger ideas here is that we can use the same backbone for a lot of subsequent tasks. And we can lock it in advance and hopefully get it approved in advance for what it's doing, if that is this parcelization. And then we can apply it later on, and we have an easier time showing that validate whatever task we're working on. And as more tasks add to the basket, we will get more and more traction for this kind of backbone. And also the domain experts are very happy working with these parcelizations, which you can visualize, you can understand. And yeah, I don't know what kind of models and problems you guys are working with, but I think the approach can be applied in much of your fields as well. And hopefully this parcelization thing will work also for your problems. So that was all I had to say. Before questions, I should also say that we're hiring in the team I'm part of right now. So if you're interested in these kind of problems, you can speak to the AstraZeneca booth later. So that's all for me. Is there any questions or?
Thank you. So actually the stego, was that a head that you added on the dyno backbone?
It was, but that one I consider as part of the backbone as well, because that one also, it's a black box model, even though it's a much smaller one, and it's trained self-supervisory as well. So okay. They're part of the backbone, but they are the heavy duty and the lightweight part of the backbone, I would say. So
what kind of head did you actually add here?
Yeah, so the heads we used here was the very simple thing about fusing several parcels. That was the head model. It was just the idea of let's merge these parcels and we get the segmentation. Very simple model, very easy to explain. And for the view detection, it was KNN.
Right, and that reminded very much of Maria's approach for the snoring, that you have sort of a zero-shot approach on a pre-trained model.
Yeah, that's true. Yeah. There are connections between all these.
Snoring and hearts is the same thing. No. Right. So can you quantify like how much less annotated data you actually need for these segmentation tasks due to the self-supervised pre-training?
We haven't done that yet, but we could definitely quantify how much data we need for certain precision when it comes to this list of parcels to use, for instance. So we will not need as much data, of course, but it will also be possible to quantify that and see like to what extent the precision changes.
Right, because the whole approach is to reduce the amount of segmentations that you need the doctor to do, I guess.
Exactly. And this will, of course, be different for different subtasks as well.
Okay. So how many segmented image did you actually train the segmentation model on then, this fusing of parcels?
Yeah, so in this case, it was around 10,000.
Okay.
But we don't need that much in reality.
Okay.
But the dataset was available. So.
Okay. Do we have more questions from the audience? So then I will squeeze in one more. So what is actually the point of how were the doctors using these results?
So we presented two specific examples of problems, and those in turn would go into the medical parameters they calculate. So typically they use these segmentations for different parts of the sequence, like the end diastole and end systole typically, and they compare the volume, they calculate the volume for these segmentations. So they will use, they will do calculations based on these that they will then acquire the number they're looking for.
Okay, to check the health of the heart in order of the volume.
In different ways, exactly, okay. And that depends, of course, on the kind of analysis they're performing.
Okay, I think it's fascinating stuff because the general approach applies to many other computer vision problems.
And not only computer vision. I mean, the problems we have here might not be as augmented in other places, but they exist in basically every problem. So if I'm trying to sell something to you, it's Alan. Like.
But I don't think you need to call it anything. Particularly, it's a very general.
Alan.
Yeah. It's a very general approach.
Yes.
Yeah, that you pre-train a model and then you lock it and then you. fine tune on some head for your specific tasks.
And I
Right.
guess the main difference between what is usually done is that we're not fine-tuning a new neural network model, and we're not fine-tuning the last layers of the current neural network model. The fine-tuning is on a very intuitive model that people can understand it and that can be communicated. And that's the big difference.
Okay. Okay. Yeah, that makes sense.